Over the next series of examples, we're going to look at more examples of optimization. In addition, we're going to learn how to graph the functions. It's important that you learn how to graph functions. In our lecture handout, we have a summary of what we learned in the concept videos, but we're going to jump straight to example 1 and learn how to take that information on optimization and where the maxes and the mins are and stretch that towards graphing of a function. So for example 1, we're going to be looking at the function y of t is equal to negative t cubed plus 75t. If this seems like a familiar function, it's because it is. We went through it in the concept videos, in which we optimized it to determine that the local minimum was at -5, -250, and the local maximum was at 5, 250. Now, in this example, our focus is going to be on graphing this function. And looking at the critical points is but one element that we look at when we're graphing. I'm going to determine these critical points that we have right here, this -5, -250, and 5, 250, just as a review, but you can skip ahead if you already remember how to get those critical points. So for that review, to determine our critical points, I would take my first derivative of the function, -3t squared plus 75. We would then set that first derivative to be equal to 0 and solve for the corresponding t values. So I'm going to move 3t squared over to the other side of the equation by adding 3t squared to each side. So that 3t squared cancel out here. I'm left with 75 is equal to 3t squared. I then divide both sides by 3 so that the 3's cancel out here. I'm left with 25 is equal to t squared. I then take the square root of each side so that I can eliminate that squaring of the t. So I get plus or minus 5 is equal to t. So I know I have two t values, plus 5 and -5. I then determine the corresponding y value by substituting these t values into our original equation. Y of t is equal to -t cubed plus 75t. So I would have y value for when t is equal to -5. I have -5 cubed plus 75 times -5, giving me -250. And then I would have y when t is equal to plus 5, and that would give me +5 cubed plus 75 times +5, giving me +250. And thereby I determine my two critical points, -5, -250, and +5, +250. I then determine which one is a minimum and which one is a maximum or potentially a saddle point using my second derivative test. So that I look at my first derivative given right here and do the derivative of that first derivative to get the second derivative. So that gives me -6t. For my coordinate -5, -250, I would substitute that t value of -5 into my second derivative. And that gives me -6 times -5, or +30. When I have a positive second derivative for a critical point, it means that in that region, it's concave up. The critical point was determined for where the slope was 0, so we can see that this is a minimum, or local minimum. For the coordinate +5, +250, again, I substitute that t value of +5 into my second derivative equation, and I get -6 times +5, giving me -30. This would be a concave down region because the second derivative is negative. I'm examining the point where the slope is 0, meaning that this would be a maximum, that coordinate. And I can thus determine which critical point is a local min and which critical point is a local max. Now, many of you may know this, many of you may not know this, but a cubic expression takes on this sort of shape, either this shape or alternatively this shape. So it's not surprising to me that I have a min and a max. And I already kind of know that it's going to fall into this shape because I know that the min followed where there was a -5, and I know that the max was where there was a +5 as opposed to this shape right here. Now, in addition to where my local min and my local max are, there are some other coordinates I'm interested in being able to note on my graph. And those are my horizontal axis intercepts. So in this case, my horizontal axis is my t-axis, so those would be my t-intercepts. I have t-intercepts, or my horizontal axis intercepts, when my y value is equal to 0. This is my y-axis. You can see along this axis, my y value would always be 0. Inversely, I also want to know where my y-intercepts are, my vertical axis intercepts. In this case, they would be y-intercepts, as we have a function y of t. And that's going to be when t is equal to 0. As you can see along this axis, t is equal to 0. So let's start with that y-intercept value, as it's a fairly simple one to calculate. I take my original function y of t is equal to -t³ plus 75t. That's my original function. And what I do is I substitute t is equal to 0 into that function to determine my y-intercept. So y, when t is equal to 0, is going to be -0³ plus 75 times 0. It's going to be 0. So what this informs me of as well is that I cross that y-intercept at 0 when x is equal to 0. I have a coordinate 0, 0 there. And again, I know that I have my max when t is equal to +5, and I have my min when t is equal to -5. Now, determining my t-intercepts is a little bit trickier. It might not be that doable with hand calculations for all functions. So our t-intercept, we take that original function y of t is equal to -t³ plus 75t. But this time we're saying our y value is equal to 0. So we're saying 0 is equal to -t³ plus 75t. So now the only way to solve this is through a little bit of factorization. So I'm going to factor out t. So I get t times -t² plus 75. I can rewrite this as t times 75 minus t². And what I know is when either one of these factors is equal to 0, then I would get y is equal to 0. I need to multiply it by 0 in order to have the result be 0. So I have the solutions t is equal to 0 as one possible solution, and the other one is 75 minus t² is equal to 0. Trying to solve for the t values for which that would apply, I'm going to move t² over to the other side of the equation. I have 75 is equal to t². Let's give myself a little bit more space. And then I take the square root of each side, and I get t is equal to plus or minus the square root of 75, or plus or minus 8.66025, and it goes on with decimals. So now the nice thing at this point is that I've got a pretty good idea of the range of t values that I'm going to be looking for. So I know that to get my intercepts to be included, I need it to range between -8.66 and +8.66, and I probably want a little bit beyond that when I do my graphing. So why don't we make our graph between -10 and +10? And within that, I know my y value here would be -250, and my y value here would be +250. So why don't we give it a y range of, say, between 250 and -250. I can even go beyond that, maybe to 300 to -300. So now working with my graph, I know I want to plot my min at -5, -250. I want to plot my max at +5, +250. I know I have my y-intercept at 0, 0, as well as one of my x-intercepts, and I have, or I should say t-intercepts, habitually call my horizontal axis intercepts my x-intercepts, apologies. I also know that when I have t is equal to -8.66 roughly, that I have an intercept there, meaning my y value would be 0. And similarly, when I have +8.66, I would have a y value of 0 as it's another intercept. So now looking at this, I've got my coordinate 0, 0 right here. I'm going to go 2, 4, 5 right here, and then vertically, if I make this 50, 100, 150, so that's 100, 200, this would be 250. So I can go 5 to 250 right here. That would be another coordinate. Similarly, I've got 100 or -100, -200. So this line would be -250. It's a -5 over here, and that will be my local min. So I have my local min and my local max plotted out. And then I have these intercepts to plot out. So I have my 0, 0 over here. I've got 5 to 50 over here, -5 to 50. And then I have 8, 9, so it's probably somewhere right around here for 8.66. So that's going to give me my 8.66 there, and I've got 8, 9 over here, so it's probably somewhere right around here. That's going to give me my -8.66. And from here, it's a bit of connect the dots. So I'm going to do this the best I can freehand. So I have 8.66, 0 here, and -8.66, 0 here. And I've covered the shape of my graph. Of course, it goes on in both directions, so I can just draw an arrow. But I have graphed the most important features of this function, and I can just leave it right there. Now, I always think it's a valuable exercise to try graphing by hand. You can do it digitally, but on your tests, you will be asked to graph at least once throughout the year by hand, so it's good to practice doing it by hand. This question referred to a second page and said, tell me which graph this is. So looking at that page, we can see that we've got that S shape going on over here where it crosses through the 0, 0 mark, where our horizontal and vertical axis right here at 0, 0. So this, of all of our graphs, this would be the graph that represents the function -t cubed plus 75t.